I'm going to talk to you today about what is an explosion. And you might think that there's going to be lots of loud bangs, and you'd be right. And you might think that there's going to be a bit of shrapnel, and you might be right. And you might think that somebody's going to get blown up, and you'd be wrong. We're not going to blow anybody up. So today I'm going to talk to you about what an explosion is. And an explosion is just defined as a rapid expansion. Okay, things get bigger very quickly, and they often give out some energy as well. Okay, so I've got a balloon here, and this balloon just has air in it. So if I drop it, it just falls. Okay, and so I'm going to make an explosion. So I've got a paper clip, and I'm just going to stab the balloon, and we'll get a bit of an explosion. Okay, so ready? So that was an explosion, because all the air in that balloon, when I popped it, suddenly got an awful lot bigger. And there's some shrapnel. Okay, so that's what an explosion is, a rapid expansion. So what I'm going to do this morning is I'm going to show you some explosions, and I'm going to show you some stuff which scientists have used to make explosions. And the first thing I'm going to show you is this stuff. Now, this stuff is basically gunpowder. Now, it's not actually gunpowder because I don't have a license to make gunpowder. Okay, so this is as close to gunpowder as we're allowed to make in schools. And what I'm going to do is I'm just going to pour this gunpowder onto this little tray. And I'm going to set fire to it. Now, it's not going to make a big bang, sorry, but I want you to look very carefully at what it does do. And I'm going to show you a chemical equation in a minute to show you what it does. And some of you people might understand what's going on in the chemical equation. Some of you might look at it and go, I'm looking forward to learning about that. So gunpowder's very, very old technology. Okay, so gunpowder was around for thousands of years and is very useful. Now, what I want you to look for two things. I want you to look for evidence that it's expanding, it's getting bigger, and I want you to look for evidence that it's giving out some energy as well. Okay, so just light this splint. Sometimes these wooden splints are a bit reluctant to catch fire. Anyway, there we go. So, I'm going to set fire to the gunpowder. So look for evidence of expansion and evidence of energy. And there'll be an excellent smell of fireworks now. Okay, so could you see evidence of expansion? Could you see it getting bigger? With all that smoke coming off. And any evidence of energy? It's on fire. It's catching fire. So that's gunpowder. Now, gunpowder, here's a chemical equation. Ooh, so gunpowder has potassium nitrate, sulfur, carbon. So potassium nitrate, sulfur and carbon, that's the mixture for gunpowder. And when it burns, so we've got what, 21 molecules at the beginning. And then when it burns, it makes potassium carbonate, potassium sulfate, carbon dioxide, and nitrogen. And it makes 5, 10, 16 molecules. But the important thing we're looking for here is these little letters. Okay, so these all have an S by them. What do you reckon S stands for? What about further back? Go on, Motherer. It's a solid. Okay, so all of these are solid. Down here we've got some more solid. You see all that smoke? All that smoke is solid. Can you smell it? You might be able to start smelling it. All that smoke is solid. But then we make G. What do you reckon G stands for? If S is solid, what's G? Gas. Absolutely right. And gases take up a lot more space than solids. Okay, so that's why the gunpowder expands, because it's making a lot of gas. But that solid is a problem. It's not expanding as much as it possibly could. So I'm going to show you another good explosive. And another good explosive is in this balloon. Now, some of you might think that the balloon has helium in it, because when you go to birthday parties, you might get balloons with helium in, and some of you might undo the stopper, take a breath of helium, and then speak with a squeaky voice, because helium is less dense than air, and so therefore your vocal cords can vibrate faster, and if they vibrate faster, you have a squeaky voice. Now, you have to be really careful if you do that at a birthday party, because if you're breathing helium, what you're not breathing is oxygen. And you kind of need oxygen in order to live. So breathe too much helium, and you might find that you are feeling a little bit ill. That's my advice, don't breathe too much helium. Anyway, this isn't helium, this is hydrogen. Okay? And hydrogen is a much more reactive element than helium, but it is also less dense than air. In fact, I'm going to stand this up here. So again, I'm going to set fire to this. Now, this will catch fire when I give it some heat and burst the balloon, and the hydrogen in the balloon will react with oxygen in the air. So I want you to look for evidence of energy being given out and evidence of an expansion. Now I'm going to stand a little bit away from this one. This is going to be a bit louder. It's absolutely fine to scream. If you want to stick your fingers in your ears, that's fine too. But let's have a look for some energy. Okay, so it'll only react when the balloon actually pops. Oh, come on. You're wooden. You're supposed to burn. There we go. Okay, you ready? Well, that was quite good, wasn't it? Yeah, and any evidence of some energy being given out? Did you feel the heat of that? Yes. Did you feel the heat of it nearer the back? A tiny bit. Maybe we need to put some of these a bit closer to you later on. So yeah, a lot more energy given off there. Now, the trouble is, And here's the equation for that reaction. Trouble is, this one's not great, because this one has 3 lots of gas, and it makes water. Now, water is normally a liquid. Obviously, it was a bit hot then, so I didn't get a fountain of water coming out of it. But you don't get an awful lot of expansion, but what you do get is a lot of energy. In fact, that reaction has so much energy that they can use it as rocket fuel. So here I have a rocket. Okay, it might look like a little plastic bottle to you, but it is a rocket. And inside this rocket, I filled it with 2/3 hydrogen and 1/3 pure oxygen. And here, the hydrogen and the oxygen are mixed together. So we don't have to wait for the balloon to burst for this one to catch fire. Okay? Now this one will be loud, and I hope that the rocket might fly. Now, if it flies and lands near to you, don't pick it up, okay? And don't do what somebody did a few years ago and picked it up and said, oh, I wonder if it's still hot round the edge. And rather than just touching it to see if it was still hot, she decided, I know, I'll use my lips to see how hot it is. And of course, then she got a blister on her lips. Now, of course, you are far too sensible to do anything silly like that. To be honest, I thought she was probably too sensible as well. Clearly not. Anyway, I'm just going to set fire to the splint. And whilst that's burning, I'm going to try not to set fire to me. And I'm just going to take the bung out. There we go, there's the water. And I'm going to say, now this is going to be loud. Oh, come on. Okay, let's see if it flies. Was that loud? Was there some energy given off then? Was there something, did it fly? So there was some expansion. Didn't quite get into space. But that mixture can be used as rocket fuel. That's pretty cool, isn't it? So, anyway, so we've had gunpowder. Gunpowder was good. It gave off some energy. It had a bit of expansion. But it gave off a lot of smoke as well, so it wasn't as good an expansion. We've had hydrogen. Hydrogen gives off a lot of energy, but we don't get brilliant expansion. So what I've got here is some gun cotton. Now, I made this the other day, and this might look like normal cotton wool, but it isn't. It's cotton wool which has had a bath in concentrated nitric and concentrated sulfuric acid. So we get a bit of a nitration reaction coming along there, okay? And so this is really good. Now, the story goes, I don't know how true this is, the story goes that the person who invented this was a chemist who had a lab. In fact, he didn't have a lab, he was just using his kitchen to do some chemistry experiments. And he did this whilst his wife was out at an evening do. And he spilt some concentrated acid on the floor, and he used his wife's apron to mop it up. And then apparently, after he'd mopped it up, a spark from the fire hit the apron. And this is what happened. So watch for expansion, watch for energy, watch for smoke. Lots of energy then, wasn't there? Not much smoke, and there's not very much of that cotton wool left. Okay, just that little bit there is all that's left. And so this stuff, when this reacts, so here's our cotton, our nitrated cotton. So that's solid, but that, so just 2 molecules of that, all the products of that are gases. So we've got this solid that turns into gas, and we've got, what, 22 molecules of gas there from 2 molecules of solid. Huge amounts of expansion. Now, if I could put that at the bottom of a rifle and then put a bullet in front of it and set it off, then it will give that bullet loads of energy and the bullet will go flying, which is pretty cool. So that's gun cotton. Now, explosives are used for all sorts of things. They're used for weapons. They're used for dynamite, for blowing up rocks in quarries and things like that. That's quite useful. They're also used a lot in fireworks. So what I'm going to do is I'm going to show you a video of some fireworks going off. These are fireworks which I set off for my mum's birthday the other year, but I must say that I didn't make the fireworks. Okay, so we bought the fireworks and we're just going to watch them because fireworks are great. Fireworks, chemistry in the sky, loads of explosions going off there. And whilst we watch that, we might see if we can accompany those fireworks with the 1812 Overture, and we might see if we can accompany the 1812 Overture with some live explosions. And let's see how this goes. So, last one. And that's what's in an explosion.